Hi everyone, so today I want to talk about what's called the Henderson-Hasselbach equation, and it's a neat little equation that tells us for a weak acid what the pH will be if you know the concentration at equilibrium of the conjugate base and just the concentration of the acid. If you know that and you know the pKa, you can know the pH. Alternatively, it can be used to prepare buffer solutions, which is pretty important in like biology and some chemical reactions where you need to keep the pH at a certain level. Buffers work nice, and it comes from this equation, how you prepare them. You basically say, okay, I want the pH to be this amount. I know the pKa of this weak acid is some value. And then I get the log of, if I subtracted over pKa, I'd get the log of the ratio of the conjugate base and just the acid, right? And you can use that to determine how much of each do you have to add. Usually like the conjugate base will be a salt like sodium A, potassium A, over that amount of acid, which, you know, if it's an organic acid, for example, it's usually a crystalline solid. So if we know, right, some, at least like 3 of the variables we can find, or even 2, right? We can find how much we either need to prepare a buffer or what pH that buffer will be at. So, and it's for just and this one would be for the Henderson-Hasselbach is for a monoprotic acid system. If you had a diprotic or a polyprotic system where, let's say, you have more than one acidic hydrogen, this wouldn't change. You would just have 3 Henderson-Hasselbach equations that you would have to use and take into consideration. Usually you just make some simplifications saying, okay, well, it's not going to go any further than I think it is, right? Or you just have to pick the right Henderson-Hasselbach. We try not to make things too complicated. So let's get into how we derive such an equation, right? Because it's kind of important to see, okay, well, I know the equation, I know it works, but where does it come from? So what we have to do here is first set up an equilibrium expression for this reaction. Assuming that water is a liquid and not a gas or anything, we can exclude it from the equilibrium. So we're going to say that Ka, the dissociation constant of the acid, is equal to, and we know up here we're going to use the concentrations of these guys, where the denominator will just be the concentrated of the acid and not the concentration of the water, right? Because it's a liquid, it doesn't have a concentration. So let's go ahead and set some things up here. Okay, so for the top, it's going to be the concentration of H3O plus or just H plus, and then the conjugate base. Notice that their coefficient is 1 and 1, so we're not going to raise it to any exponents, right? So this is going to be H plus, right? You can, and it should be noted these are interchangeable, right? H plus and H3O plus. Usually the H2O is just the carrier of that proton, but we think of it as a free proton because it's so easily able to be ripped off by some sort of base, right? And then let's look at A minus here. Okay, so we have A minus, right? This is going to be the top, the conjugate base and the conjugate acid. Or sorry, not the conjugate, well, I guess, yeah, the conjugate acid, right? Or just the hydrogen ion concentration. And we're going to put that all over the concentration of our acid. Okay, so how we get the Henderson-Hasselbach is we do an equivalent statement that still keeps these things as Ka equals this. We're just going to take the negative log of both sides. And this, you'll see, is the biggest step to seeing how we get the Henderson-Hasselbach equation. So if we take the negative log of Ka, right? So we're taking the negative log of the constant that tells us how much this acid dissociates equals negative log, and I apologize, I'll have to scoot over here, equals the negative log of the hydrogen ions, and then that conjugate base, and that is going to be all over the concentration of our acid. So this is what we have. Now, where do we go from here? It is quite simple. We're going to use log rules to kind of explain this. So let me come up here. It's very important that you understand these log rules. If I have a log of A times B, right, and that's inside the logarithm base 10, right, this would be the same thing as writing log 10a, right, log base 10a plus log base 10b, right? It's a totally fair thing to say, right? Because we know that if you ever took algebra, I think you would learn this in algebra 2, right? When you add logs together, you can combine them. The same also works if, let's say, we wanted to do something with like a denominator or a quotient, right? A divided by B, right? This would be equal to log of A minus log of B. So it's important properties to understand, right? These two, when we go through our next step in the derivation of the Henderson-Hasselbach equation, and it's going to be in here. So we're going to group this as its own log, negative log of the H plus. That maybe should ring a bell, but we'll kind of explain what that means in a second. But then we have a concentration of the conjugate base over that acid. So hopefully you can see it here. Maybe. If not, we'll go through it. So the next step is to say, okay, negative log of Ka, and we're going to equal this to, and my notation is going to get interesting here. I'm going to say negative and then put the log, do the log rules in parentheses, and then distribute the negative after, just to make sure we don't make any weird sign errors. We could split this up to say log of H plus, right? And then we could add that to the quotient of the log quotient of A minus, and I should be putting brackets around this, of HA. Okay, and then there should also be brackets around the H plus. Don't forget, it's concentration we're talking about, not pressure or something weird like that. So now that we have found this, let me now kind of just distribute the negative in. And while we do the step where we distribute the negative in, let's simplify this side, right? Negative log of Ka. Well, we know that P of X, right? Or like pH, pKa, right? Anything px is going to be negative log of that thing in question, right? So keep that in mind, that this is how we define the little p in front of whatever species we're talking about. It's just the negative log of that. And we can call this pKa. So pKa is going to equal, and this would be, if we distributed the negative in, it would be negative log of H plus, so this would be pH, right? Negative log of hydrogen ion concentration. And then this is going to be minus the log of A minus over HA. And if you notice, there's a little simplifying step we can make to really just get the Henderson-Hasselbach. Let's move pH to this side and move pKa to this side, right? We're going to get pH equals pKa plus the log of A minus or the conjugate acid, or conjugate base, over HA. So all we really did there was kind of switch these around, right? This would be negative pH minus pK minus log of this, right? We just drop the negatives, right? Because -1 is a constant term on all sides. Just divide by it on both sides, and you're going to notice that we get the nice Henderson-Hasselbach equation, a very, very helpful one indeed. So hope you guys enjoyed. Have a wonderful day. Bye-bye.